Hi, I'm Ansh, and today I'm going to be talking about different number bases. The way we count is using powers of 10 that, when summed, represent a number. For example, if we take 352, we can see that the 3 here represents 3 times 100, the 5 here represents 5 times 10, and the 2 here represents 2 times 1. When we sum these, we get 352. So 352 is 3 times 100 plus 5 times 10 plus 2 times 1. Or 3 times 10 squared plus 5 times 10 to the 1 plus 2 times 10 to the 0. Sorry. The digits we use are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So this is pretty cool and all, but what's cooler is that we can use different bases for the powers to sum the numbers. For example, instead of using powers of 10, we could use powers of 2, or powers of 3, or powers of 19, or whatever number you want. Using different powers, let's say we use powers of n, this is called counting in base n. Now, counting in base n has some things you need to remember. Really, it's more like two things. So you use the digits 0 through n minus 1, kind of like how we use 0 through 9 in base 10, which is our counting system, and it uses powers of n, which, yeah. So, for example, if we have 1, 0, 0, 1, 0, 0 in base 2, by the way, we represent base n with a little subscript of n. If we want to convert this to base 10, all we have to do is figure out what the digits stand for, and then we sum them up. This 1 here, well, let's start from the 0. This represents a power of 2 to the 0, and there is 0 of it. Likewise, this 0 over here represents 2 to the 1, and there is 0 2 to the 1s. This 1 represents 1 2 to the 2s. And so on. This is 0 times 2 to the 3, this is 0 times 2 to the 4, and this is 1 times 2 to the 5. So if we sum all of these numbers that we have here, we'll get what this is in base 10. So we have 1 times 2 to the 5, plus 0 times 2 to the 4, plus 0 times 2 to the 3, plus 1 times 2 squared, plus 0 times 2 to the 1, plus 0 times 2 to the 0. This is equal to 32, plus 0, plus 0, plus 4, plus 0, plus 0, which is equal to 36 in base 10. Now, you don't need to use the subscript for 10 unless you really need to clarify what bases is. Usually, people will assume you're talking in base 10. Now, we've seen how you can sum up the numbers, or what the digits represent to get what the number is in base 10. But let's say we go back to 351. We go to 351. What if we want to convert this to base 7? 351 to base 10 is 1 in base 7. So we look for powers of 7 that are close to 351. Well, 7 to the 0 is 1. That's not really close. 7 to the 1 is 7. Not close. 7 to the 2 is 49. Getting better. 7 to the 3 is 343. So we can see that we can include exactly 1 of 343 if we want to make 351. 2 would be greater than 351. Now, since we already have 1 343, we can't include a 49. So we have 0 49s. And now we have 1 7 and 1 1. So 351 in base 10 is 1 0 1 1 in base 7. Now, some more observant watchers might be thinking what we do for bases bigger than 10. For example, let's look at base 12. So let's start with the digits. We have digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. But these aren't digits. 10 and 11 are 2 digits. So what do we do for digits that, have more than one digit in them? We use letters. Letters already have an agreed upon order, and they're one symbol each. So we substitute 10 as A and 11 as B. So a digit of A would represent 10 of a power in a base. Okay, now let's do a problem. The problem is, let n be a positive integer and d be a digit such that the value of the numeral 32d in base n equals 263, and the value of the numeral 324 in base n equals the value of the numeral 11d1 in base 6. What is n plus d? So we start this by writing these in equation form. 3 to d base n is equal to 263 in base 10. And 3 to 4 base n is equal to 11d1 base 6. So what we start doing is expressing these as the sum of their powers. So we know that the 3 represents 3 times n squared, the 2 represents 2 times n, and the d represents d times 1. So, and the 3 here represents 3 times n squared, the 2 here represents 2 times n, and the 4 here represents 4. The 1 here represents 1 times 6 cubed, the 1 here represents 1 times 6 squared, the d here represents d times 6, and the 1 here represents 1. So we get that 3n squared plus 2n plus d is equal to 263. And 3n squared plus 2n plus 4 is equal to 6 cubed plus 6 squared plus 6d plus 1. We move the 4 to this side. 6 cubed is 216, and 6 squared is 36. So what we do is we subtract 4 from both sides, and we also subtract 6d from both sides. So the 4's here cancel out, and the 6d's here cancel out. So this equation stays the same. Let me just copy paste it over. Three n squared plus 2n plus d equals 263. And now our new equation is 3n squared plus 2n minus 6d is equal to 216 plus 36 minus 4 plus 1, which is equal to 249, if I'm calculating this right. Let me just... Yeah, 249. Now we subtract this equation from this equation, and we get that the 3n squares cancel out, the 2n's cancel out, and then we get d minus 6d is equal to 263 minus 249. So d plus 6d is equal to 14. 7d equals 14, so d equals 2. Now we plug this back into 3n squared plus 2n plus d equals 263. Now that we have d, we can calculate n relatively easily. 3n squared plus 2n plus 2 equals 263. 3n squared plus 2n minus 261 is equal to 0. This is just a quadratic, and the quadratic can actually be factored. The factorization of this quadratic is 3n. Hold on, let me just figure out the factorization. Yeah, so this quadratic factors as 3n minus 29 actually plus 29 times n minus 9 equals 0. You can double check my factorization, and we see that the solutions are n equals negative 29 over 3, or n equals 9. Now, let's just think about what n is for a minute. N is a base. A base, like, by common sense, a base can't really be a fraction or negative. So n equals negative 29 over 3 is out, which means that n is 9. And we got that d is 2 earlier. So we wanted n plus d. N plus d is 9 plus 2, which is equal to 11. Scrolling back up to the answer choices, we see that option B is 11. So our answer is option B. This problem is an example of when you get a base problem, that sometimes you should just expand it into the powers and see what you can do. Alright, that's it. If you enjoyed this video, Mustang Math has lots more, so please try to watch them. Okay, thank you.